Convert to bits. Decimal to binary conversion is done through various methods. One of the methods to convert decimal to binary is by dividing the given decimal number recursively by 2. Then the remainders are noted down till we get 0 as the final quotient. After this step, these remainders are written in reverse order to get the binary value of the given decimal number. A number system is a mathematical way of representing numbers using a set of digits or symbols. There are different number systems like the decimal number systems, the binary number system, the octal, and the hexadecimal number system. These are identified with the help of the pack they have. Initial permutation, or IP. As we have noted, the initial permutation happens only once and it happens before the first round. It suggests how the transposition in IP should proceed as shown in the figure. For example, it says that the IP replaces the first bit of the original plaintext block with the 58th bit of the original plaintext, the second bit with the 50th bit of the original plaintext block, and so on. This is nothing but jugglery or bit position of the original plaintext block. The same rule applies to all the other bit position. Expand right. Recall that after initial permutation, we had two 32-bit plaintext areas called left plaintext or LPT and right plaintext or RPT. During the expansion permutation, the RPT expanded from 32 bits to 48 bits. Bits are permutated as well, hence called expansion permutation. This happened as the 32-bit RPT is divided into 8 blocks, with each block consisting of 4 bits, then each 4-bit block of the previous step is then expanded to a corresponding 6-bit block. Example is per 4-bit block, 2 more bits are added.
After the expansion, permute DES use the XOR operation of the expanded right selection and the round key that both the right section. In a substitution shifter, any character of the plaintext from the given fixed set of character is substitution by some other character from the same set depending on a key. A ordered agreement for the elements of a set a function and both a to 1 to 2a and onto mapping of a set to itself.
XOR left, a Boolean logical operation that is widely used in cryptography as well as in generating parity bits for error checking and fault tolerance. XOR compares two input bits and generates one input bit. The logic is simple. If the bits are the same, the result is 0. If the bits are different, the result is 1. Rotate halves left 1 is a circular movement of an object around an axis of rotation. A three-dimensional object may have an infinite number of rotational axes. Extract bits. A bits, short for binary digital, is the smallest unit of data in the computer. A bit has a single binary value, either 0 or 1. Half a byte, 4 bytes, is called a nibble. In some systems, the term octet is used for an 8-bit unit instead of byte.
This is one of the examples of data encrypted system or DES, works on bits or binary numbers, the zeros and ones common to digital computers. Each group of 4 bits make up a hexadecimal or base 16 number. Binary 001 is equal to the hexadecimal number 1. Binary 100 is equal to the hexadecimal number 8. 1001 is equal to the hexadecimal number 9. And 1010 is equal to the hexadecimal number A, and 111 is equal to the hexadecimal number F. This works by encrypting groups of 64 message bits, which is the same as 16 hexadecimal numbers. To do the encryption, this uses keys where also apparently 16 hexadecimal numbers long, or apparently 64 bits long. However, every 8th key bit is ignored in the DES algorithm so that the effective key size is 56 bits, but in any case, 64 bits or 16 hexadecimal digits is the round number upon which DES is organized. The plaintext message, "Your lips are smoother than Vaseline," is in hexadecimal. If we encrypt this plaintext message 64 bits or 16 hexadecimal digits at a time using the same DES key as before, we get the ciphertext. DES is block cipher, meaning it operates on plaintext blocks of a given size 64 bits and returns ciphertext blocks of the same size. Thus, this results in a permutation among the 2 times 64 read keys as times 2 to the 64th power possible arrangements of 64 bits, each of which may be either 0 or 1. Each block of 64 bits is divided into 2 blocks or 32 bits each. A left half block L and a right half R. This is the division only used in certain operations. The 64-bit key is permutated according to the following table. Since the first entry in the table is 57, this means that the 57th bit of the original key becomes the first bit of the permuted key K+. The 49th bit of the original key becomes the second bit of the permuted key. The fourth bit of the original key is the last bit of the permuted key. Note, only 56 bits of the original key appear in the permuted key. There is an initial permutation IP of the 64 bits of the message data M. This rearranges the bits according to the following table, where the entries in the table show the new arrangement of the bits from their initial order. The 50th bit of M becomes the first bit of IP. The 50th bit of M becomes the second bit of IP. The 7th bit of M is the last bit of IP. This results in a final block for n equals 16 of left 16 and right 16 that is in each iteration. We take the right 32 bits of the previous results and make them the left 32 bits of the current step. For the right 32 bits of the current step, we XOR the left 32 bits of the previous step with the calculation f. It remains to explain how the function of f works. To calculate f, we first expand each block Rn -1 from 32 bits to 48 bits. This is done by using a selection table that repeats some of the bits in Rn -1. We'll call the use of this selection table the function e. Thus, Rn -1 has a 32-bit input block and a 48-bit output block. We have not yet finished calculating the function f. To this point, we have expand Rn -1 from 32 bits to 48 bits using the selection table and XOR EV. The result with the key CAUAYAN, we now have 48 bits or 8 groups of 6 bits. We now do something strange with each group of 6 bits. We use them as addresses and tables and called S boxes. Each group of 6 bits will give us an address in a different S box. Located at that address will be a 4-bit number. This 4-bit number will replace the original 6 bits. The net result is that the 8 groups of 6 bits are transformed into 8 groups of 4 bits. The 4-bit outputs from the X boxes for 32 bits total. If S is the function defined in this table and B is block of 6 bits, then S1B is determined as follows. The first and last bits of B present in base 2 a number in the decimal range 0 to 3 or binary 00 to 11. Let the number be I. The middle 4 bits of a B represent in base 2 a number in the decimal range 0 to 15 binary 000 to 1111. The block the output S1B of S1 for the input B. For example, for input block B equals 0, 1, 1, 0, 1, 1, the first bit is 0 and the last bit is 1. Giving 0, 1 as 0 is 0, 1. The middle 4 bits are 1, 1, 0, 1. This is the binary equivalent of decimal 13. So the column is column number 13. In row 1, column 13 appears 5. This determines the output. 5 is binary 0, 1, 0, 1, so that the output is 0, 1, 0, 1. Hence, S1, 0, 1, 1, 0, 1, 1 equals to 0, 1, 0, 1. The DES algorithm turns a 64-bit message block M into a 64-bit cipher block C. If each 64-bit block is encrypted individually, then the mode of encryption is called electronic code book or ECB mode. There are two other modes of DES encryption, namely chain block coding or CBC and cipher feedback or CFB, which make each cipher block dependent on all the previous messages blocks through an initial XOR operation.